Unfortunately, I have to cut a little bit to send you to lunch on time. I'm going to skip some of the introductory slides and I will jump to this one. So in a similar way as we define the laminar flame speed, which is the speed of a flame propagating in a quiescent mixture, where the entire structure is propagating at a constant speed, say SL. We want to define, and some of the earlier slide that I skipped, question, is there such a thing as the turbulent flame speed at all? But so say there is, and there are some argument given there, we want to define it as the propagation speed of a turbulent flame into something which is like a quiescent mixture for laminar condition, which will be a turbulent flow that have zero mean. In other words, doesn't have a mean flow in the direction of propagation. And then, if that's the case, then if the turbulent flame remains statistically or propagates under statistical stationary condition at some speed st, we call that the turbulent speed. Or put it in a slightly different way, if the mean velocity of the incoming flow is st, of course with some perturbation have zero mean, and if you retain the flame statistically stationary at some location y, then the mean velocity will be the turbulent flame speed. The main idea behind which are held up to today about turbulent flame go back to Damkohler. And Damkohler, in fact, influenced the concept of turbulent flame speed and its scaling. He talked about small and large scale, and I'm going to skip some of the small scale, and I will jump into the large scale. So the large scale turbulence, or what we refer to as corrugated flamelet today, this is basically the idea that he said. So in this picture where the turbulent flame is held statistically stationary in a cross-sectional area A, the mass flow rate, the incoming mass flow rate is the density rho u, the area A, multiplied by some mean velocity, which is going to be the turbulent flame speed if this is held statistically stationary. So this is the mass flow rate. If this same mass is consumed through this turbulent flame, then, and since every section of the flame surface, say delta AT, propagate at the laminar flame speed SL, then the total mass consumed is going to be the mean of, or if you like, all the segment delta AT, which is going to mean of that corrugated surface, multiplied by the density rho u and SL, which is the propagation speed. And so when you equate those two, you get that the ratio of the turbulent speed to the laminar speed is the ratio of the corrugated area to the cross-sectional area, okay? This is one of the ideas, and that have, in fact, influenced a lot of the discussion or the advances in the literature. In particular, experimentally, very often people can measure the ratio area and try to equate it to the speed to determine the turbulent speed, and or express the ratio of the turbulent speed to the laminar speed. So those 2 points. Well, Damkohler went on to argue, how am I going to determine this in general. He made some argument based on like every small segment, it's like a Bunsen flame, and he tried to determine the area ratio, and he came to such a scaling. And later on, Shelkin had a different scaling. Again, I want to skip that, but what I want to say is that most of the literature thereafter trying to write the turbulence speed relative to the laminar speed, which is going to be some coefficient, of course, depending on various physical parameter, and the turbulent intensity V prime, which is the RMS of which is the fluctuation velocity relative to the flame speed, raised to some power. So for example, Demkohler N was 1, Shell can say that some condition it's 2, some condition is 1/2, whatever. That's the point. Okay. I wanted to, first of all, make some, or review or revise some of this discussion. So if we follow the same discussion as we did a minute ago for Demkohler, but now argue that the flame speed of every segment is not the flame speed, the laminar flame speed, but is affected by flame stretch. So it's SF, not SL, which is affected by stretch. Then, and if you equate the two, then now first of all, the consumption of all those segments is going to be rho u, and the mean of the product of the area time the flame speed, which is not the laminar flame speed. So then the ratio is of turbulent to laminar is going to be the ratio of the mean of the turbulent area times the local flame speed divided by the section here. Of course, if all segment propagated the laminar flame speed, you obtain the Demkohler result. But the idea is that the turbulent flame speed may include effects that are other than just the increase in flame area, which may be due to the Markstein lengths and due to stretch that are not accounted in the previous discussion. And we can determine the turbulent speed in a calculation in two ways. One is going to be the mean incoming flow if I retain the flame statistically stationary, or I can compute it from this relation, right? Okay. Just a minor comment: if the flame is, folded and so on, then when I add the different segment of the area, I have to account that for a given location, I may have more than one segment, and they have to enter properly in the calculation. Okay, it's a minor comment. And again, I will rely on this same hydrodynamic theory. The flame is an interface, so the assumption is that the flame is so thin that the turbulence does not affect what's going on inside the flame. Is this reality? Not necessarily, but it's the model that we describe. I am not totally convinced that it's always not the case. In other words, there is no definitive proofs that that turbulence affect very much the internal flame structure to the extent that it changed the turbulent speed tremendously. It may happen under some condition, of course, and it's logically to expect that, but it's not, and it's neither shown experimentally nor numerically that it does that. But anyway, argument, different ways. In this model, then, we have the following parameter. We have the intensity of the turbulence, V prime. We have some turbulent length scale, L, which I will probably not talk about today much. And then we have the combustion parameter, which is the Markstein length and the density ratio, right, in this model. Note, by the way, maybe again I failed to move on with different things. I didn't emphasize too much this. I did say, though, that the Marx-in length is affected by different parameters. In fact, you see, the nice thing about it, that it lump all the mixture properties, diffusion properties, density ratio, and so it lump them into one number. That number can be changed by different things. So it's an important or an interesting quantity, and people have measured Marx-in lengths on different conditions. And some of the early ideas was that you can perhaps use them to describe, I don't know, a local structure of a turbulent flame, assuming that it's a strained flame, and you tabulate that, and you use that as your small scale if you're doing LES or such calculation, which is, an idea, but it's important to know that this Marx-in number entered those pictures as well. So I will skip those, you can read them. So what we are interested is, therefore, we have a turbulent flow coming here with some fed, it's created independently in a different, usually it's created in a long box. You create turbulence. There are different numerical method to create synthetic turbulence, as we call it. And you create a long box, and then you you feed it, so to speak, into your box here at a certain speed, V inlet. And the idea that we had, that we can, with a flow control way, we can control the velocity. In fact, we can also control the intensity of turbulence that you have here, which can be, of course, once you generate a turbulence, it have a intensity and a scale, which is given, not given, but computed as part of what you have created. And you can control the V prime as well with a controller. So, for example, this is a PID controller. You see that V prime can be kept to whatever you want no, this is the flame position for different V prime. And you see that you can control it over time to retain, so you can retain the flame at a fixed position this way, okay? By changing the inlet and for different V prime. Similarly, you can control the mean velocity, which eventually is going to be the turbulent speed by this controller. So that's the idea, and you can also do it in 3D, and this is the flame that you can see when in a 3D configuration. So anyway, this is part of the idea. So you can now compute the turbulent speed either as the mean inlet velocity or incoming velocity, or by this relation. And I don't know if I'm going to show any comparison, but all the results that we got using this, you get more or less the same value. Not identical, but basically same value. So this is just to show you that what happened due to the turbulence. And what you see here is essentially the vorticity field, and it's not the entire vorticity. There are methods to show the important vorticity. I think it's a Q criterion, it's called, for those of you familiar. I don't know, my students know more about it, but anyway, this is the idea. The top figure and the bottom figure are the same, except that the top one show, I think, the shape of the flame. You see here the shape of the flame, just the shape rather than the entire flame, but the flame is the surface here. What I want you to see, and that's why I run it again, that the flame is often folded, and sometimes there are also segments of the flame that unburned pieces that detach. When you get too folded, they detach. So we were able to capture all these even in this relatively simple model. And now I want to focus on a few things because I will not have time to do everything I want. Oh, my watch died. Okay. So I'm looking at the time. So I want to show you here what happened if for two different Markstein numbers with the same intensity. Remember that the Markstein number from the discussion earlier today, the small Markstein number are more cause an instability. The flame is more unstable, right? So you see at 0.08, okay, the flame due to the turbulence is slightly perturbed, okay? But at 0.018, smaller Markstein, you see this cusp-like behavior, which is like the signature of the Dirichlet instability, okay, which is absent in this picture. And this is also true. This is also true in 3D. It's not a movie. It's just to show you that the flame here is more mildly corrugated, and here it's more significant. And so the point here that I want to make is the following. There will be similar to what we have learned from stability theory, that there is some kind of critical inverse Markstein number or Markstein number that separate between the stable flame from the unstable flame. There will be some effect on the turbulent flame, and I will call this subcritical and supercritical, but don't expect that the stability criteria would be the same for the turbulent flame as for the planar laminar flame that we discussed, but it's in about the same range. And so this is a value from the linear theory, which the inverse should be about 25. This is below 25, this is above. And by the way, the number are big because the inverse tend to jump up, but if it's Markstein number, they're usually relatively small numbers. What you see here is that it's overall on the average, at least at the low intensity, is nearly flat, you know, whereas here they tend to have this cusp behavior that you expect due to the instability. And in fact, you can examine the PDF of the flame position or curvature, and in this case, it's more symmetric, right? The position. In this case, it is not symmetric because of the intrusion into the burn gas that is more likely to, the position is more likely to be in one direction than another. And for the curvature, again, for the subcritical, the flame due to turbulence is curved up or curved down at nearly equally chances, or nearly equal probability, and that's why it's more symmetric. Whereas for here, you have highly curved peak region, which tend to be seen, you know, extending here quite to the left quite a bit, okay? So that's an effect. I put here the laminar case just to remind you what they come. When intensity is quite high, it seems like those distinctions try to not to exist anymore. As you can see here, in the high intensity region, you know, you don't see much difference between the sub and supercritical. And if you measure this flame brush thickness, delta, which is something like you can obtain it from the PDF distribution of the flame position. And what you will see is that after a while, they tend not to be affected by so much by the Markstein number. All the picture tend to, well, I mean, if we could carry those calculations long enough, maybe they will tend to one constant. We don't have that, but they certainly. But what is more important is that you see the subcritical one here goes to, delta goes to 0 when V prime goes to 0, because the flame, when in the absence of turbulence, will flatten out. But in those supercritical cases, then the flame never flatten out, because even when turbulence intensity goes to 0, you reduce the turbulence, the flame is unstable due to the Darien-Landau instability, so it will create a cusp. So taking the ratio ST versus SL is not really always appropriate. Maybe it should be ST versus the capital U that I used to describe the propagation of the Darien-Landau flames. Okay. This is just to show that you will get, also more, sort of curved surfaces for the subcritical case and more sharp cusp for the supercritical case. How do I distinguish between the two? It's the pressure. Remember that the Markstein length is proportional to flame thickness. You increase the pressure, you decrease the Markstein length, so you make it more unstable. And even though V prime is approximate, it's small, nevertheless, the pressure is high, so this is more hydrodynamically unstable. Similarly on the right, and this also. So the turbulent flame speed now that we calculated, we also saw the same effect that I mentioned to you before, that as you go to small intensity, it's not only the thickness, the flame brush thickness that go to 0 or not 0, but also the speed go to a value here, which is more related to the propagation of the cusp-like Darien-Landau flame. And so we refer, or one can refer this as a Darien-Landau enhancement in the turbulent case. And if we scaled, as I told you, ST with UL, not with SL, UL being the propagation of the cusp-like flame, then you see they all go to 0 as expected. So it seems that at least what I promote is that this scaling is perhaps more appropriate in this case. This is just, by the way, some of these results are 2D, some of them are 3D. Of course, 2D are easier than 3D. And, but here what it shows is another point that I want to make, is that if you graph ST as opposed to the turbulent speed as opposed to the area ratio, you will find out that they don't align with the straight line, which means that they are proportional, but they are always below, indicating that in fact, the turbulent speed is, or the area ratio overestimate the turbulent speed. Again, it's a comment on the original result of Dam-Kohler. So if you write the ratio of the turbulent speed as I suggested earlier, and if this mean can be written as the mean of AT multiplied by the mean of SF, which is strictly speaking not necessarily correct, but it's approximately right, and it was verified numerically, then what you get is the area ratio, but also multiply by a coefficient which is a result from stretching. So this stretching effect for Lewis number bigger than 1 cause a reduction in speed relative to the area ratio. I want to comment something that I had a sentence in one of my lectures. I forgot perhaps to over-explain it, but maybe I'll explain it now in a few minutes. I did mention it in different ways. Actually, it was in red because it was important. The hydrodynamic theory is only work currently for Lewis number bigger than 1 or bigger than some critical value. The reason for this is what I showed in the discussion of instability earlier today. What we have seen is that, can you see this? Or, yeah, okay. So what we have seen is that diffusion effect can stabilize the short waves, and so the mathematical discussion of this model is complete and had no issue. But for Lewis number below 1, we saw that the growth rate grow as such. And I told you that numerically we could have, numerically people have, DNS have obtained the stabilization of very short wave. Unfortunately, our current model does not describe this behavior. And so the hydrodynamic model doesn't have a mechanism to stabilize the very, very short waves when the Lewis number is less than 1, which means that it's not appropriate there. In fact, it's not only inappropriate in the simplest way if you have, you have an equation that blows up. And so it needs stabilization of very short waves too. So therefore, the limitation of the discussion of the theory is for Lewis number bigger than 1. And as you notice, I never said anything Lewis number. Now, Lewis number less than 1 is very interesting, I know. Many people work on this because it's like clean hydrogen. If the theory was completed, it would have led to sufficient guidance for numerical simulation. But at the moment, I know that there are some groups try to identify this in different ways, but I will not talk about it more. So anyway, this is here, that's why it's limited to L positive. Positive meaning Marx-in length positive, which is equivalent to Lewis number sufficiently bigger than 1. So the stretching effect caused a reduction in, so the area ratio under such condition will overestimate the turbulent speed, okay, if you just measure that. And here you can see the mean flame speed relative to SL, which is basically a result of the stretching, or that's this term here. It's presented for different marks in length. And here you see the mean stretch of the turbulent flame, and you see how the mean stretch increases with intensity. In fact, it's an interesting comment. Some of the early calculation have suggested that curvature is the more important factor, which is not true. Well, at least I am not convinced by my calculation. It turned out that a curvature, the effect of curvature is not as strong as the effect of straining, okay? And I don't remember what came here. Here it is. You see how curvature effect for increasing intensity, whereas strain show a more significant effect on the flame, okay? This is the straining effect and for different Marx-in number, but this is the comparison between curvature and strain. One more, I wanted to discuss one more item, and perhaps I will more or less summarize there. So this is taken from 5 very 5 consecutive time calculations of the turbulent flame. It was taken in 2D. So delta T is very small, T1, T2, and so on. And you see the creation of a pocket, first of a flame that get folded, and then it pinch, and then it separate, and then the part of the pocket of unburned gas burn, and then disappear completely. Okay, that's what you see here. Now, and this is the same, but with more time steps in between. And what I want to show you is that you see here is the flame area up to the pinching, and of course there is a drop as a result of that because there's less area. Not only the folded area increases the area, but also the pinched area. But there is also a drop in the turbulent speed, okay? And when this happens very frequently, then you would expect that the turbulent speed will slow down. And it is a possible explanation for the leveling of the rate of increase of the burning velocity at high turbulent speed, or something which is known as the bending effect. I didn't show you the introductory comment today, but basically people believes that that generally speaking, the turbulent speed, say, tend to reach some kind of leveling, and this is known in the literature as the bending effect, okay? It doesn't keep on increasing despite the intensity being larger and larger. So it seems like that may provide an explanation that high intensity, you'll have more folding and more of this pocket formation, and therefore there'll be more and more of drop of the turbulent speed, and possibly it will level it off. Some comparison of some scaling law that were proposed in the computation. Note that they also appear as V prime to some power. There is the stretching effect, and we have done a distinction between low intensity and moderate intensity. I didn't talk about high intensity because high intensity will affect the flame thickness. Is not really compatible with our model, or our model is not compatible with that. But you see that there is a difference in that. And there are some experiments that show somewhat similar trend. The numbers seem to be not too far from each other. So that's really what I wanted to. There is a bit of discussion of spherical flame that we did as well. Now the picture is different. You create turbulence in some box, but you limit your calculation to a smaller box so that the effect of the boundary don't play a role. And well, this is more observation. This is laminar condition. This is cellular forms. Again, laminar condition. And you see this is under turbulent condition. It's a significant intensity, so, okay. And this is some of the calculations that we do. Again, you see the strong vorticity field. Those are vortices, blue and red, counter direction. You see the flame circles that have those folds, pockets that form. So it's quite complicated. This is not the entire computation region, as I said before. I don't remember what I wanted to show, and I will probably rush this quickly, that you can see different behaviors. In low turbulence intensity, you see a lot of cell splitting, like in the laminar condition. So the flame appears laminar, but is driven by Bernoulli liner instability. And in fact, it shows a little bit of, resistance to turbulence. Okay? And then it show more splitting and collapsing of cells. And then you see the more high intensity. Here, U naught is the intensity. I didn't say that. So the more higher intensity show similar to what I was showing you for the 2D case, formation of those cusps and so on. Okay, I want to try to summarize things. I don't know where. Well, no, okay. I know, I'm sorry, I added too much. Almost the end. So what was the end? Oh, I had a comment about the end. Okay, so anyway, I wanted to point out here that there are some interesting aspects that one is able, with simplified theory, to discuss. So we were able to argue that ST over SL is not necessarily AT over L. There are effects of stretch that play a role. We're able to discuss the effect of curvature versus strain on the effect of turbulent speed. We're able to discuss perhaps you have to be aware of the fact that when you reduce the intensity, things don't go laminar flame and planar flame and so on. And that, so I show a few of this, and that the Bernoulli liner instability play a significant role, at least in the low intensity limit, because at high intensity, turbulence is stronger, and those things get hidden there by the. So it's almost the end, because the end bring me to bring some comments from a philosopher and psychologist. Is known apparently for the book Principle of Psychology. And what does it say? The first response to a new theory is that the ideas are wrong. You know, if you do constant density approximation, they'll tell you it's nonsense. Combustion is not about constant density approximation. This, well, I'm not only talking about this, but that's an example. Later, when the ideas are found right, the response is that they are unrealistic or insignificant. And finally, when they all say that the idea is probably right and important, oh, but they were already known. Thank you very much. I appreciate your attention. I'm sorry that here and there I had to cut some of the material, but you have some of the information. I think reference as well. If you need any reference, something that you didn't see, you can write to me. I'll be more than happy to respond. Not always the next 5 minutes or the next hour, but you will get an answer. I believe, I trust, I mean, I will. Just say where you're from, why, and so on. Don't send me an email. Why is this? I am so-and-so, you know. Sometimes I get those emails, which are a little annoying, because how do I know who is that person? Ask me a question. Just say who you are, what you are doing, why are you doing. Thank you very much. I really enjoyed talking to you this week.